The last video ended when the tape drive in my main production camera failed. The solution I chose was to ship it to the manufacturer to be repaired properly. It wasn't cheap, but it wasn't anywhere near what I was expecting for it to cost, and it was less than a quarter of what this thing would have cost to replace. I'm really excited to have it back, and so is Caboose, because it means more wet food. My estimate came in a week earlier than quoted. The repair also happened a week earlier than quoted. Because of the expedient manner in which my repair was handled, I'd have paid any price so that I could get back to making videos again. The outpouring of support from all of you is both appreciated and unexpected. I read and appreciate every last one of your comments and private messages. I'm proud to have such a loyal base of subscribers who are filled with so much generosity. But I told you, I got this. I know that if I solicited donations, that I violate my partnership agreement, and I can tell by the hundreds of comments that if I opened that door, you guys would have sent way too much money. All I ask from you is for your time and attention and nothing else. Of course, I always appreciate it when people hit the like button and share my videos. That always helps Jafro out big time. The first matter of business, though, is to see what I can salvage from the 2 tapes I shot prior to the failure. This footage is what remains, and I've decided to go ahead and use it despite its segmented nature. I was laying out some parts and the tools I was going to use for several of the upcoming tests, like my Felpro Permatorque head gasket, a couple of dial gauges, some straight edges, some feeler gauges, a digital caliper, some magnetic stands for the dial gauges, I have a few different kinds, a set of test springs from the local hardware store. I found these to be a perfect fit over the valve stem seals and only 1 pound of pressure each. I'm saving them for another video though. Don't ask why I've got Romex and dikes. Builder's choice, I guess. You'll see soon enough. I've got my crank pulley, and it's useful for what we're about to do. Can anyone guess what this imaginary part might be? Because it's not here yet. I'll save it for the next video. Make sure you have your crank pulley bolts cleaned up and ready to go. In the next video, we're messing with head bolts, so I've got a 10mm Allen head socket that fits the factory bolts. If you're messing with a 6-bolt, this is another tool you have to own. Grease? We don't need no stinking grease. I also bought a piece of plexiglass when I bought the springs, but then there's this particular item picked up from the aviary aisle of my local pet store. They wouldn't put this on it if someone somewhere didn't use this for the wrong hole. I just need the graduated syringe, that's all. What we're going to witness today is what you need to do if you want to calculate your compression ratio. Your pistons aren't the only factor that determines how much compression each hole produces. Parts selection, as well as machining performed on all of those parts collectively, are what determines what each hole is going to make. In order to calculate your compression ratio, you need to know several specifications for your parts. You want to have your bore, your stroke, your head gasket's compressed thickness, where all the pistons line up with the deck surface, the dish volume on top of your pistons, and the total combustion chamber volume. Some of these numbers are easier to measure than others depending on how you feel about doing math, but we're going to keep it simple so that anyone can do this with their parts. These are the variables in the equations that we need to solve in order to calculate the compression ratio. You'll notice that all of the calculations involve the exact same formulas. They just use different variables. We need only to fill in the blanks. Swept volume is your engine's calculated volume based off of its bore and stroke measurements. I know both of mine already and will save the calculations for later. Add to that the head gasket volume. You calculate your gasket's bore diameter area times the crushed thickness of your head gasket to get the volume of the gap between the block and the head. Then add the piston-to-deck volume. This is where the piston lands relative to the block's deck at the top of its stroke. If it lies below the deck, the volume calculated is positive because it adds to the volume of that particular bore. If it lands above the deck, then this number subtracts from the deck volume, making it a negative number. You use the bore diameter here in your math for the piston-to-deck volume. Piston dish volume is relative to the shape of the pistons you're using. Dished pistons provide positive values, and domed pistons may provide negative values. It depends on what their fly cuts look like. All measurements are easiest to calculate in cubic centimeters. The last thing we want to know is the volume of the combustion chamber that belongs to the head. That's V5 in cc's. These are all measurements that when added together yield the total combustion chamber volume when that cylinder's piston is at bottom dead center. The number to the right in our compression ratio is the volume of the combustion chamber when the piston is at top dead center. Let's take a better look at our volumetric equation because it's really just basic geometry. To calculate the volume of a cylinder, you multiply pi times the radius to get its area in whatever unit of measurements you're using. Then you multiply it by its depth to get its volume. 3 of the values you use to calculate the combustion chamber volume are perfect cylinders, so we use this exact same equation to determine the variables for V1, V2, and V3. Easy peasy. Pi times the result of the diameter divided by 2 times the diameter divided by 2 times the depth. That gives you your volume. If your units are measured in inches, multiply that result by our first magic number, 16.387. I call this a magic number because it's an invaluable tool in this equation. All of my measurements are in linear inches, so my volumetric results are in cubic inches. Multiply any measurement that you have in cubic inches by 16.387 and you get its volume in cubic centimeters because there are 16.387 cc's in 1 cubic inch. There's another equation you can use that's simpler though. It's a technique referred to as slicing pi. It involves a second magic number. Instead of having to cut your bore in half twice, you divide pi instead. And a half times a half is a quarter. If we move this portion of the math over and slice pi rather than the bore, then we get a second magical number of 0.7854. 0.7854 is a quarter of pi, rounded to a 10,000th of a decimal place. More than adequate for our mathematical needs here. Since pi is quartered, we don't need to split our bore measurements anymore, and the math becomes a much simpler bore times stroke times 0.7854. If inches times 16.387. You can use this formula to simplify your volumetric equations instead of the longhand formula. Just remember that all of these measurements need to be in cubic centimeters for the rest of the math to work. So convert any results that you have in inches. Let's look at the bore and stroke. I already know these measurements because the 2-liter 4G63 crankshaft I selected has a stroke of 3.465 inches. And I already painstakingly blueprinted my rotating assembly in a previous video. For my example here today, we're just going to calculate cylinder number 2 for now. For number 2, I measured 3.3751 inches. So 3.3751 times 3.3751 times 3.465 times 0.7854 times 16.387 equals 508.0037 cc's. There's V1. My head gasket is a popular choice and many people have already posted its diameter and crush measurements all over the internet. I'm going to measure my head gasket, but I'm going to rely on known crush numbers from other users who have posted it because I'm not ready yet to crush my head gasket. Here we measured 3.399 inches in diameter. This gasket is known to compress to 0.039 inches thick, so 3.399 times 3.399 times 0.039 times 0.7854 times 16.387 for cc's, and we get 5.7991 cc's. There's V2. Now we're going to measure piston-to-deck height to calculate V3. I'm putting my crank pulley back on here to use as both a measurement tool and also to make turning the crankshaft a little bit more easy on myself. We need to locate top dead center and bottom dead center in order to measure our clearances because those are the only locations in its rotation where two of the pistons achieve their maximum height. I'm using my dial gauge swept through about half of its range at the highest point, and I'm indicating top dead center vertically off of the number 1 or the number 4 piston. To indicate bottom dead center of a 4G63, indicate the exact same way off of piston number 2 or number 3. This works because the 4G63 has what's called a flat plane crankshaft. The goal here is to turn the crankshaft until it measures the largest measurement you can achieve and stop. I rotate the gauge face to line up 0 with the needle so that I can make several more passes to double and triple check my measurement. Once you've got it lined up is up. You found top dead center. I used the Romex so that I could get a bright, obvious copper wire to make the pointer with. I just pulled the ground wire out of the bundle and bent it into shape with a pair of dikes so that I could use any nearby bolt as an anchor, and then bending it into position to line it up with the mark on the crank pulley. At least for number 1 and number 4 you can do this. I lost the footage where we indicated off of number 2, but you would just want to mark the pulley with a Sharpie wherever the pointer is after you zero the dial bore gauge at the highest measurement on number 2. With both 0 degrees and 180 degrees now known, you can inspect the piston installed height versus the deck. For this, low tech works best. A straight edge and feeler gauges. You place the straight edge across both parts, and if the piston lies below the deck, Measure between the piston and the straight edge, increasing feeler gauge sizes until you can't fit one of them all the way around the edge of the piston and deck. When that happens, it was the previous one that you measured with. Right here on my number 1 piston, we find 7 thousandths because 8 thousandths doesn't fit. Write that number down. Next, move on to number 4. Do the same thing until you find the right measurement. If there's any variation in the pin bore depth of your pistons, you'll get a different measurement from one piston to the next. It's best to check all 4 pistons because this is a common occurrence. This variation in piston-to-deck height is not as common in more expensive name-brand forged pistons as it is in these types of generic, no-name, non-hypoeutectic, cast non-turbo pistons. But when there are differences here, you may see a variation in your compression numbers. Here I ended up with a 15/10,000ths feeler gauge and the piston below the deck. Write down your number 4 measurement. We're just getting started. Now you want to rotate your engine to your 180-degree mark and check the clearance again. Here I find the number 3 piston actually protruding above the deck. In this situation you want to place the straight edge flat against the piston and measure both sides between the straight edge and the deck. Once you find the largest feeler gauge that fits between both sides of the straight edge on opposite sides of the piston, you have your measurement. My number 3 measurement was 3 thousandths above the deck. Write it down and move on to number 2. On number 2 I started with the 3 thousandths and it was too big. 2.5 thousandths fit on one side and not the other. What ended up working out for me was the 2 thousandth feeler gauge. So now I have my piston height numbers. Positive is below the deck and negative is above it. You can see I have 9 thousandths of an inch difference in these pistons. The measurements are only one of 5 measurements used to calculate your compression ratio, and you can only get them by assembling the parts and measuring them. There's another test necessary to calculate your compression ratio that requires assembly. After you have all of your machining and modifications completed and the head assembled with no cams in it, you need to know your combustion chamber volume. Rather than do an immense amount of math, there's really an easy way to do this, and this is where my $2 piece of plexiglass comes into play. I like to cut a piece of it a little bit bigger than the combustion chamber, and plexiglass is really easy to work with. You can just score it with a razor and break it. Then I drill a hole in the center of it, place a block of wood under the plexiglass as you drill to minimize your distortion and protect your work surface. I use a razor and scrape against the rough edges at a 45-degree angle to remove any overhanging material along the cuts, just sort of bevels the edge. And I verify that everything's gone by following it with a fingernail. An extra step you can take to produce a smoother edge would be to pass the edges through the flame of a torch. Small rough surfaces of this material will melt smooth. You just want to ensure that nothing protrudes below the large flat surfaces on either side of this tool. We're going to use both sides of it. Because the valves protrude slightly below the surface of the cylinder head deck, I like to make little fly cuts to accommodate the edges of the valve so that this plexiglass plate sits flush all the way around the edge of the combustion chamber. Also, because it's clear, it's really easy to see where to do this. Just make sure you don't move around between cuts. Now that we have this handy little tool constructed, we need to seal up the combustion chamber with a spark plug. To keep the test practical, don't use a bolt for this because a spark plug has a specific volume inside the combustion chamber as well. Next we want to level the head on our work surface with the gravitational forces of whatever planet we're from, and to begin our volumetric testing. I'm just using folded up coffee filters for this, and it doesn't matter what you use as long as you make it level. So with that accomplished, we're just going to use the measured amount of water to displace all of the oxygen in the combustion chamber using the parts we have assembled, and it will give us the exact volume of the combustion chamber we test. The graduated syringe I'm using has a volume of 10 milliliters. Because the combustion chamber is larger than 10 milliliters, I'll just count how many full syringe loads it takes until the combustion chamber is full. Water has a pretty distinct meniscus, and you want to get down and eyeball it level with the deck where it rises until it's even with the rest of the deck. To ensure that you have it right, drop the plexiglass plate down on it with the reliefs facing the valves and see if there's any air bubbles. The hole in the middle is the relief to keep the plexiglass plate from floating on top of the water if you overfill it. I went about 1/4 of a milliliter over. Then we subtract what remains in the syringe from 10 and add that to the rest of our counts. This is the exact volume of this combustion chamber in cc's. You can repeat this test as many times as you like to get it right and on every combustion chamber, but for the sake of clarity we're moving on, you get this. Testing the dish volume on the pistons is a lot like what we just did with the head. First you level the block. It's easy enough to do on an engine stand because it rotates. After I've got my rotation right, I just use a few layers of cardboard under the wheels of the engine stand until I've got my bubble level straight. and then I prepare my liquid medium. I'm sort of wasting my time here because it's well known that a 9-to-1 compression non-turbo stock cast piston is 10 cc's, but this is how the process works if you have an unknown dish volume. All the pistons have one thing in common. They go in parts that can rust if you test this using water-containing minerals like tap water does. So I'm using denatured alcohol to prevent contaminating my block. Demonstrating this procedure with room temperature denatured alcohol is almost a waste of time because its evaporation rate is so fast that it's hard to get a precise measurement. Rubbing alcohol evaporates more slowly because it isn't pure, but it won't contaminate your block. If you use alcohol of any kind for this test, freeze it first and do the test as quickly as possible. It'll slow its evaporation rate well enough to give you accurate results. You can see how fast the air bubbles form under the tiny little breather hole on the top of our little test tool. I put exactly 10 cc's of alcohol in it and enough evaporated to create those bubbles before I could cover it with a plexiglass. Oh yeah, you want your relief cuts facing up when you do this. I forgot to mention that. Automatic transmission fluid works for this too, and it won't strip your piston to cylinder wall lubrication out, but it can be messy. If you use something that strips the cylinder and ring lubrication, remember to reapply a rust-inhibiting lubricant when you're done, and cycle the engine several times. So here are all the numbers you need to calculate your compression ratio. My measured piston height is in the top left corner. I've got my head's combustion chamber volume measured for number 2. I've measured my head gasket diameter and borrowed the crush thickness from the community. We all know that the stroke for a 2-liter DSM is 3.465 inches because the factory said so. And there you've got up in the top right corner my measurements from a previous video for all of my bores. To calculate V3, we need the piston height for number 2 as well as the number 2 bore diameter, and we once again practice our equation. 3.3751 times 3.3751 times our piston height of 2/1000ths of an inch, and this is supposed to be negative, I don't know where that went, times our magic number 0.7854 and convert to cc's multiplying 16.387, and we get 0.2932. So I'm writing that one down on the board to help calculate the total combustion chamber volume. At this stage we just use the results from our volumetric measurements and add them to the rest of the mix. Rumor stated that the 63D 9-to-1 compression non-turbo pistons had a 10 cc dish volume. My pistons were 30 over, but we verified that it's still 10 cc's with the liquid volume displacement tests. That's V4. V5 is the results we achieved with the head combustion chamber measurement. We measured 41.75 cc's from my shaved 40,000ths, shrouded, recessed, valve jobbed, polished J1 Hyundai cylinder head. The rest of what follows is the easy part. Now all we have to do to get the front side of our compression ratio is add all 5 of these volumes together. So that's 508.0037 plus 5.7991 plus 0.2932, and that should be a negative number, remember? Because the piston protruded above the deck, so negative. Sorry about that, my bad. Plus our dish volume of 10 cc's plus our head combustion chamber volume of 41.75 cc's, and we get 565.2596 cc's when the piston is all the way down at the bottom of the stroke. That's what that front number is. The number at the top of its stroke is easy to calculate because it's the total volume minus the swept area, V1. To get this value, subtract V1 from your total combustion chamber volume and you get 57.2559. That's the combined values for V2, V3, V4, and V5. If you want to check your math, subtract all those values from this result and you should get 0. But we're not going to do that right now. We're going to finish the math because I don't want to distract you with that. To reduce the ratio, you divide both sides of the equation by the denominator because a ratio is basically just a fraction. When you divide any number by itself, you get 1. But on the front side, we divide the total combustion chamber volume at the bottom dead center position by the total combustion chamber volume at top dead center, and we get 9.8725. That's our reduced compression ratio for the front half of the equation. This is the number everyone talks about. There is no real way to determine exactly what your compression ratio's potential is without taking the time to do this kind of math and measurements and using real measurements that reflect all of your parts. My variables change from one cylinder to the next, so there would be variations in my results. If I wanted to take this to the next level, I'd measure every combustion chamber and every cylinder to complete my total displacement and compression ratio, but these numbers have given me all the information I need for now. Hopefully this example sheds some light on the math behind this portion of your tuning. If you know how to use this formula, you don't need expensive software or even online compression calculators to get these numbers. but by the time you do it once, you'll never forget how to do it. That's all I've got for now, but I'll be back soon with another video. I'm glad to be back in production and appreciate the time you spent here on Jafromobile. Click the like button so Caboose can have some wet food, and until next time, stay tubed.